Good afternoon, students. It's Mr. K. We're going to try this again. I know that some of you may be having issues if you have logged into the Google Classroom and saw that I posted some videos, a reading assignment, as well as a Google form assessment to fill out. I had a couple kids get a hold of me yesterday and told me that the Chromebooks will not allow you to access the videos. So I'm going to go ahead and record them on my phone and post them to a YouTube channel so that you guys can then watch them. It's a PowerPoint. It goes pretty quick. It pulls up some things and it is narrated by someone. So definitely some important things to be thinking about as we look to getting back to school, hopefully, and look at potential for industry credentials. This is definitely part of the industry credential piece, which is exactly what we're doing. So hopefully by learning some of this stuff, albeit some review, you guys are better preparing yourselves for the industry credential. So hopefully you guys enjoy the excitement.
Welcome to Chapter 1, Section 1 of the Ohio Certified Nursery Technician Training Manual, developed by the Ohio Nursery and Landscape Association. In this chapter, we will learn about soil basics. Soil has a wide range of attributes and can be defined in many ways. Listed here are some features and abilities of soil, including that it can house living organisms, support plants, decompose waste, and be used as a material resource. Soil is important because it is the foundation upon which plants grow, and plants provide food, energy, and oxygen. Soil is the integrator of all parts of terrestrial ecosystems and should be considered an essential natural resource. Once lost, soil is very hard to recover. Soil formation is influenced by a number of factors, including climate, topography, parent material, macroorganisms, and microorganisms. Soil formed on top of mountains is different than soil formed in a valley, and soil formed in a rainforest is different than soil formed in a forest. The soil formation process is dynamic and always changing, which is important to remember in relation to improving damaged soil. When exposed, the soil of the earth appears as layers, called horizons. Each horizon is assigned a letter that refers to that particular layer. D, bedrock. C, parent material. B, subsoil. A, topsoil. Topsoil is the most important horizon for plant growth. How does soil form? Trees and plants drop leaves and other organic matter to the ground, which collects on the surface. What is above the soil affects soil formation, and the collected organic matter forms another horizon, called the organic horizon. The organic horizon is referred to with the letter O. Not all soils have an organic horizon. Desert soils typically do not have an organic layer, as depicted in this image. Soils also form from the bottom up. While it may seem to defy gravity, components from each horizon will continually rise to the surface. Big rocks from the bedrock horizon will become smaller rocks and move into the parent material horizon. Rocks in the parent material horizon will move into the subsoil horizon, and so on. This means if the bedrock is limestone, the pH in the topsoil horizon will continually rise over time. This limestone wall illustrates the point. In this situation, it would be near impossible to maintain an acidic soil pH by adding an acidifier like sulfur. We would be shoveling against the tide. Here are some important points about each horizon. Topsoil is the soil nearest the surface. There is no official designation for topsoil, but it is critical to plant growth and the success of your landscape. If you buy topsoil near your location, it will likely be the same topsoil as yours, and you will gain nothing for your landscape. Topsoil should be protected when possible, especially during construction. Topsoil should be stockpiled and returned to the site once construction has ended. Soil properties are generally separated into three categories. The first category is physical properties, which include soil horizons, texture, consistency, density, and moisture. The next soil category is the chemical properties, which includes the soil's pH, cation exchange capacity, and the available nutrients. Biological properties include the presence of microorganisms and macroorganisms, nutrient recycling, and aeration. Keep in mind that the three soil properties do not behave independently. They interact with one another to affect the nature of the soil. When discussing soil properties, we'll start with the physical attributes. We have already introduced soil horizons in relation to soil formation, so now we'll discuss compaction. Some of the characteristics of soil compaction include impermeable or hard soil, which resists water and root penetration. Soil compaction also means that there is a low oxygen holding capacity and a low water holding capacity, which is not conducive to healthy plant growth. What happens when soil is compacted? First, the topsoil is squeezed down, but note that the topsoil doesn't disappear. This is important to remember when we work to correct soil compaction. We still have everything that was there before, and all the organic and mineral components remain. Soil compaction can occur any time that equipment has run over soil, particularly wet soil. Some of the most serious compaction occurs during construction. However, homes cannot be built without risking soil compaction. Plant roots need water, warmth, and oxygen. Root cells must get oxygen directly from the soil. If the soil oxygen levels reach 5%, roots stop growing, and once it reaches 2%, roots die. Oxygen is held in soil pores, and the same is true for water. Compaction destroys the soil structure and causes soil pores to collapse. Remember that when topsoil is removed during construction, it should be stockpiled and redistributed after construction to support plant growth. However, in some cases, only a small amount of topsoil is returned to the landscape, and the rest is sold. When topsoil is removed and not returned, the exposed subsoil mimics soil compaction. This picture shows exposed subsoil with only 2 to 3 inches of topsoil being returned to the site. Note the water in the equipment ruts. It hadn't rained for about a week before this picture was taken, and the water did not come from irrigation. This shows that the subsoil had poor drainage, just like what happens with soil compaction. It is very important to learn the history of a landscape site. Was it formerly farmed? Old farming techniques, such as annual plowing, can produce a compaction zone. As a moldboard plow moves through the soil, the shape of the plow drives the blade into the soil. The bottom of the blade exerts downward pressure, which produces soil compaction. Remember that the plow loosens the soil above the plow, but compacts the soil below. Years of plowing eventually produces a compaction zone that behaves like the subsoil horizon. Exactly the same thing happens with the annual use of a rototiller. This soil profile picture was taken where the land has been plowed annually for 80 years. Note the grayish layer of soil illustrated by the red band. Soil is made up of 3 different sized particles: sand, silt, and clay. When the soil is loosened by plowing or rototilling, the clay particles, which are the smallest size, can be moved by water through the soil, which is called eluviation. Eventually, the small clay particles are deposited deeper in the soil, which is called illuviation. This graphic illustrates the movement of clay particles by water and the deposition of the particles deeper in the soil. Let's look at the process of a false clay layer. Water causes clay particles to move from the upper portion of the topsoil to a lower portion of the topsoil, which produces a false clay layer. This layer is not formed naturally. The false clay layer may be mistaken for a different soil horizon, so it becomes a false horizon. The false soil horizon interferes with water penetration further into the soil, creating a perched water table. The water table is elevated, and the soil remains saturated for an extended period of time. What happens when there is a clay layer produced by farming, or a plow compaction zone, and the topsoil is removed? The illuviated soil, or compacted soil, is exposed to the surface. The resulting exposure produces a soil condition that acts just like soil compaction, or the soil condition may mimic the subsoil horizon. The following series of pictures show what happens when the false clay layer, or plow compacted layer, is brought to the surface by topsoil removal. The lower layers of soil are brought to the surface and drastically change the soil composition. This soil condition makes it very difficult to create a healthy and thriving landscape. From soil compaction, we are now going to discuss the texture aspect of soil's physical properties. Soil texture is the way a soil feels. What you feel when you rub soil between your fingers is determined by the percentages of sand, silt, and clay in the soil. Sand, silt, and clay are the mineral particles in the soil. Soil textures for the three mineral particles are gritty for sand, silky for silt, and sticky for clay. To separate clay soil from silty soil is to wet the soil and form it into a snake by rubbing the soil between your hands. If the soil stays together, it has a high percentage of clay. These graphics illustrate the relative sizes of sand, silt, and clay particles. The first sieve has a screen size that prevents sand particles from passing through, but allows silt and clay particles to pass. The second sieve has a screen size that prevents silt particles from passing through, but allows clay particles to pass. Once we determine the percentages of sand, silt, and clay in the soil, we can plot these percentages on the soil textural triangle. Note that the sides of the triangle represent the different particles, and the percentages of the particles run from 0 to 100. The percentages of sand, silt, and clay in our soil places the soil at a particular point on the triangle. This allows us to describe our soil based on its soil textural classification. Loam is considered one of the best soils, and clay is often considered bad soil due to its poor drainage. However, loam soil can contain as much as 30% clay. Clay soil does have a much higher percentage of very tiny particles compared to loam soil, and this does produce a different quality, particularly with water infiltration. There are significant differences between the way water infiltrates loam soil compared to clay soil. This may cause you to think that clay soil is compacted soil. Water readily infiltrates loam soil, and water takes much longer to infiltrate clay soil. Actually, water may at first run off the clay soil until it slowly infiltrates. Soil texture has a direct impact on water movement and retention in the soil. This graphic shows the relationship between soil texture on the x-axis and the water in the soil, shown on the y-axis. Gravitational water is the water that remains in soil after all water has been drained by gravity. Field capacity is reached when all the water has drained from the soil by gravity, but the soil is still moist. Water available to plants is the range of water concentration in the soil that will support plants. Permanent wilting point is reached when the water in the soil is held too tightly to the soil particles to be available to plants. Clay holds on to more water than sand after the water has been drained by gravity. Why is that? Water is held on the surface of soil mineral particles. It does not penetrate the particles. This means the total amount of water held on the particle is affected by the size of the particle, which means we must consider the volume of the particle. So, the amount of water held on the particle is related to the surface to volume ratio of the particle. How can we make particles hold on to more water? How can we increase the surface to volume ratio? We will use this table to illustrate how to increase surface area. The exposed surfaces of the table are on the top, bottom, and sides of the tabletop and legs. How do we increase the exposed surfaces of the table? We cut the table into pieces. We have exposed new surfaces while at the same time decreasing the volume of each piece of the table. We have increased the surface to volume ratio. Imagine the uncut table as a sand particle and the cut table pieces as clay particles. Clay particles have a greater surface to volume ratio. Collectively, they can hold onto more water than sand particles. Remember that the three properties of the soil interact. Let's look at how the chemical properties of soil can affect the physical properties of soil. Before we discuss chemical properties, we need to review some chemistry basics. Pictured here is a hydrogen atom. The center of an atom is called the nucleus. The nucleus has a positive charge because it consists of a proton, which has a positive charge, and a neutron, which has no charge. Spinning around the nucleus is an electron. The electron has a negative charge that keeps it attracted to the nucleus, but the speed of the electron prevents it from falling into the nucleus. Electricity is simply the movement of electrons around nuclei. When an atom has too many electrons, the entire atom will have a negative charge and is called an anion. When an atom doesn't have enough electrons, the entire atom will have a positive charge and is called a cation. What happens when an anion meets a cation? To illustrate the point, we will use chlorine, which is an anion, and sodium, which is a cation. With magnets, remember that ends with opposite charges attract each other, and ends with the same charges repel each other. Since opposites attract, the chlorine anion will attach to the sodium cation to form a new substance called salt. This is a chemical reaction, and the salt is now called a molecule, since it's made of two or more atoms. Now, let's look at building another molecule starting with an oxygen atom. The oxygen atom carries two negative charges, so it's an anion. Sometimes the oxygen atom will attract two hydrogen atoms. Hydrogen is often found without electrons, so it is a cation. Oxygen and hydrogen combine to form a water molecule. Two atoms are now stuck together because they are sharing electrons. This is called a chemical bond. Water molecules are bipolar. The hydrogen has a positive charge, while the oxygen end has a negative charge. The hydrogen end has a positive charge, while the oxygen end has a negative charge. This means that water molecules behave like tiny bar magnets. When the opposite ends attract and the molecules will stick together, it is called an electrostatic bond. Electrostatic bonds are very weak, just like with magnets. Electrostatic bonds are observed as surface tension. Drops of water on a table look like bumps because the molecules stick together. Capillary attraction is also based on water molecules sticking together, which is how water moves up plant stems. The surface of clay particles have sites that are negatively charged, so water molecules can become attached to clay particles. The positive end of the molecule attaches to the negative sites on the clay particle. Remember, this is a weak attachment of molecules. Why does clay hold on to more water than sand? Clay particles have a greater surface to volume ratio compared to sand. Water molecules become attached to the clay particles through electrostatic bonds. The reason we are covering this process in such depth is because it affects soil incompatibility. If we have a layer of clay directly over a layer of sand, water will take time to infiltrate the clay simply because it takes longer for the water to move around the small particles. However, once the water has drained through the clay by gravity, the clay will hold on to more water than the sand. The clay will remain wet, creating a perched water table. If a layer of sand is placed directly over a layer of clay, the physical nature of the clay will first act like a barrier, keeping the sand wet. However, once the water drains through the sand, the clay becomes wet and remains wet longer than the sand. The soil surface will appear dry while the subsurface is wet, which is a condition that can cause overwatering. The rapid gravitational drainage of sand may tempt landscapers to add sand to clay soils in order to enhance drainage. However, there is great risk to adding sand to clay. The tiny clay particles may become packed around the large sand particles, producing what is commonly called the concrete effect. It requires a minimum of 60% sand added by volume, based on the total volume of the final mix, in order to effect a change in drainage without risking an inhibition of water movement. Root balls should be examined to make certain there is not a soil incompatibility issue with the surrounding soil. To solve this problem, create a transition zone using organic matter. The physical quality of clay may cause us to conclude that clay is bad. But is it? To answer, we need to explore cationic exchange capacity and why it's important. Soil test results show the cationic exchange capacity, CEC, of the soil. Soil particles are surrounded by negative attachment sites. Each clay particle has a fixed number of negative sites, just like a bus has a fixed number of seats. This clay bus has 30 seats. The passengers on the CEC bus are cations and represent important plant nutrients such as potassium, K, calcium, Ca, and magnesium, Mg. The CEC measures the total capacity for the soil to hold on to and exchange cations. CEC does not measure the capacity of individual clay particles. The process is similar to measuring the total seating capacity for a fleet of buses. The higher the CEC, the higher the capacity for soil to hold on to nutrients. The lower the CEC, the lower the capacity for soil to hold on to nutrients. Usually, the higher the CEC, the higher the clay content of the soil. Soil used in certain nursery and greenhouse production systems do not include clay. These soils are generally referred to as soilless media because there is no mineral component in the soil. They are designed to maximize root growth and minimize soil moisture problems. However, using soilless media means nutrients are easily washed from the soil and they require an almost constant infusion of nutrients. In a landscape, it is not practical to constantly supplement the landscape with nutrient. So, we return to the question, is clay really a bad soil? Soil test results also let us know about the pH of the soil. So, what is pH and why is it important? pH is measured on a scale that runs from 0 to 14, with 7 being neutral. pH values above 7 are alkaline, commonly called basic, while pH below 7 are acidic. Here are the pH values for some common substances. This concludes Chapter 1, Section 1, Soil Basics.
Woo! What do you guys think? That was exciting. Now, I have a second one that I'm going to record right after this. It goes more in depth on soils. I know you're so super excited about it, but that will conclude everything you'll need to know for the first assessment that we have. What I'm going to do after I post this one and it's not raining out is I'm going to do an actual video with me in it, which will then highlight the second part of our assignments for next week. The way it'll work, kiddos, while I gotcha, is you will have 2 graded assignments a week while we are gone at minimum. One is probably going to revolve around some reading and an assessment, kind of like we're doing now. In the second portion, I will do my very best to get you guys out and about, probably utilizing your cell phones, maybe taking some pictures, and then explaining what we're looking at. So I know it's not ideal, but we're just going to do what we have to. So again, I'm going to start this second video here in a couple seconds, and they'll be posted to the Google Classroom. I hope you guys are all doing all right. I know this is not ideal, but practice your social distancing, wash your hands, and hopefully we'll get to see everybody soon. Take care, kiddos.